Okay, so we began graph theory. We started to define graph, describe the basics of graph. Today we are going to formally describe different types of graph, because in many applications we require different types of graph, different modalities and different capabilities of them. So a lot of just big words, a lot of not big words, but a lot of words, a lot of terms and concepts we are going to discuss. Nothing deep, nothing complex, right? Very simple. So pay attention to it. We have a lot of ICPs related to these things, and then maybe some kind of a quiz, okay, a small quiz in the middle, just so that we test that do we understand things or not. So this is what we talked about graph. A graph is two things. Actually a collection of two sets. Okay, one set is called the set of nodes or set of vertices. The other set is a set of subsets of size 2 of the vertex set. Each element in the edge set is an edge, is a pair of two elements, two vertices, and they are called edges. Okay, so in this graph there are 4 vertices. I have named them, labeled them, so we can write about them, we can talk about them. One, A, B, C, D, these are 4 vertices, so the set of vertices is A, B, C, D, and then there are edges. Edges are pairs of elements of V. Okay, so A, B, A, C, A, D, you cannot have an edge named A, X, right? Cannot have an edge P, Q. In this particular case, you can't just write a pair here. It has to be a pair, a subset of size 2 from the previous set. Okay, so there is a slight abuse of notation. This notation we use for ordered pairs, right? These are not ordered pairs, these are unordered pairs, but we use the ordered pairs notation because it's standard and should be clear. So in different applications we require different graphs. The graph that we described so far is actually what's called undirected simple graph. Right. So when we talk about directed graph, it will be clear, an undirected graph, and when we talk about non-simple graph, then it should be clear that we really appreciate why the simplicity, what is simplicity. Okay. So here the graph is what we talked, it's two things, a set of vertices and set of edges. Edges are unordered pairs, subsets of size 2 of V, okay, 2 subsets of V. That's only, this is how it's drawn, this is how it's pictorially depicted. Obviously for large sets, a lot of vertices or a lot of edges, just like last time we talked about the web graph, the internet graph, the Facebook graph, the Twitter graph. Twitter doesn't work like that. The Facebook graph or the Instagram graph, the power infrastructure graphs, a lot of the biological graphs, chemical networks, pipeline networks, highway networks, railway networks, all of those are these kind of things where the vertices are, I don't know, stations or Facebook users, and edges are friendships. And in highway network, vertices are intersection between two roads, and edges are the road segments joining two nodes or two intersection points. These are what we call undirected simple graphs. Okay, so a few terms related to these, and then we will go to different types of graph and we will review the whole thing. Okay, so order of the graph is a word used for it, order of the graph, because a graph is two things, right? So I can't say what is the size of the graph, right? Or what's the magnitude of the graph. There are multiple dimensions to the magnitude or to size, the volume of the graph, right? How big is it, a big graph or a small graph? So that's why we use two distinct words for it. Order of the graph is the cardinality of the vertex set. Okay, size of the graph is the cardinality of the edge set. Is this clear? So order of the graph is the cardinality of the edge set, and size of the graph is the cardinality of the edge set, the number of edges. Okay, number of vertices, number of edges, two things. So now we will say, okay, this is a big order graph and a small size, and this one is more large order and large size, or small size and large order, or something like that. Okay, so just to test our understanding, let's see. Suppose I have a graph of order n. What is its maximum size? Okay, Just need the definition of size, definition of order, the definition of graph. So can you translate what is this question asking for? Can you rephrase this word? Rephrase the, yes please.
If a graph has n vertices, then how many edges will it have?
How many edges will it have? No.
At most.
Yeah, how many edges, what's the largest number of edges it can have? Okay, what's the maximum possible number of edges that any graph on n vertices has? We call it a graph on n vertices. Okay, a graph on n vertices. So what is that? Again, it's a simple cardinality question. Okay, there is no concept, just the definition. How many different edges are possible? How many different edges are, how many edges are possible? So how would you come up with the answer? No answer, just tell me how would you come up with the answer? When I ask you how many edges are there, first thing you do is translation, right? So how many you know. Then, yes?
Sir, from an unordered set we need to pick two elements, so it can be n choose 2.
Yeah, so yes, what do you want to say?
So we can imagine this as a triangular numbers problem where we have n edges over there and then.
So when you answer a question, the first thing you do is you translate the question, right? So when I say how many edges are there, or how many edges can be there, what is the word that needs definition here? What is the word that needs some, how many edges, right? So what is an edge? What is an edge in an undirected simple graph?
It's a line connecting two vertices.
No. What is an edge? There is no line, okay? Yes, what is an edge? Yeah, edge is the two subsets of V, right? It's an edge, it's two subsets of V. Okay, that's how we define a graph, right? You see two things, V and E, no lines, no laddu, no lakire, okay? It's just two subsets. So the question actually means what is the maximum number of two subsets that an n set can have? Okay, how many subsets of size 2 are there for this set V which has cardinality n? So what is the answer?
N minus 1.
No, n choose 2. N choose 2, that's the definition of how many subsets of size 2 are there for an n set, right? So how many ordered pairs are there, or how many, is this clear to everyone? The answer to this question is n choose 2. Again, please understand this thing, okay? You have a quiz next time, and it's just this type of questions, okay? I only ask very basic questions. I take words seriously, it's a language course, I just do the language substitution, okay? We know two subsets, we know how to count the cardinality of that, how many two subsets are there. I gave you a set, that's a ground set, you're picking two subsets of it, just that we call it edges now, okay? So the number of two subsets, the number of total maximum, is it clear why it's n not n minus 1? That it's n choose 2, right? The number of, how many subsets of size 2 can you make from this set V whose cardinality is n, this n choose 2, right? This is the definition of n choose 2. Okay, so the next thing is pseudographs. Now these are not simple graphs, right? These are the graph where I'm allowing, so it's again two things, every graph is two things, set of vertices, set of edges, right? Here the vertex set is the vertex set, the edge set is allowed to have, the pairs are pseudo pairs, right? So A is allowed to be one of the element of the edge set. X is also can be part of edge set, right? So it's not just pairs of distinct elements, these are pairs, it could be repeated also, okay? Okay, so this is in picture it will be, so self loops, these are called self loops, they are allowed, right? There can be an edge between D and D, right? So DD is a pair in the edge set, BB is not a pair in the edge set, CC is and AA isn't. Is it clear? It's called pseudographs. Not used very widely, but sometime when we do, so for example, if you do algorithm, you will see the min-cut algorithm, which is called the H contraction or summarization, graph compression, graph summarization. Is always this self loops are necessary. You have to implement those things. So we allow it, right? And it's no big deal. I just say That's why these pairs or two subsets, these are not the strict two subsets, right? Not subsets of cardinality 2. Here I allow a pair to have repeated elements, okay? And there is multigraph. Here actually this is the set of vertices, set of edges. The set of, it's not really the set of edges, it's a multi-set of edges, right? A pair can appear multiple times, okay? So it will be multi-set. So here the edge BC will, BC, the pair BC will appear twice in the edge set of this graph, in this E, right? In this E, the edge BC, BC pair could appear twice, or CD will appear 3 times, AB will appear only once, okay? So it's not a set, it's a multi-set, okay? Again, not used very frequently, but sometimes becomes important, and then it's not a big deal. Just like for sets, we mentioned, we talked about multi-set, but just because occasionally we feel the need to write about it, so life becomes very easy if you give things a name and develop some kind of a vocabulary around it, okay? So this is also, we just added, this is perhaps the last time in this course you will hear about this, okay? Most probably, yeah. Okay, so now let's some more terminologies. Again, we are working with undirected simple graph. Now onward, when I say let G be a graph, I would mean, unless I've qualified it or I've used some prefix with it, when I say graph, we mean undirected simple graph, okay? If I mean pseudograph, I will say pseudograph. If I mean something not undirected or non-simple, then I will say that word. But for graph, generally would mean undirected simple graph, okay? So here is the undirected simple graph. I've labeled the edges and the vertices, right? Just like we can give any subset a name, let A be a subset, let B be a subset, so it becomes easy to talk about, right? So I've just given each subsets of size 2 a name, I've written them on top. It's a subset is drawn, depicted by a line segment between the two vertices, okay, that are contained in the edge. So there are 4 edges in this graph. What's the size of this graph? What's the order of this graph? What's the size? 4, right? So size of E1 is AB. This is the set, this is the pair, this is the unordered pair that is contained in the edge set, right? So it's E1. We say A is an endpoint and B is an endpoint, right? So these two are called endpoints. Now this picture makes sense why they are called endpoint. If for this road, this is the one endpoint or this is the other endpoint, right? B and C. For E4, C and D are the endpoints, right? We say E1, the edge E1 is incident on A and B, okay? It's incident on A or B, or the edge E1 contain A and B, right? And because of this pair, when a pair is there in the edge set, we say the pair is adjacent. Otherwise, the pairs are not adjacent, right? So, is B and D, are B and D adjacent? Is B adjacent to D? No, right? Is A adjacent to D? Is A adjacent to B? Yes, so that's adjacent, incidence, these 2 words, endpoints, 3 words, okay? Adjacency is the most important word. Yes, please.
इस वाले जो ग्राफ में we have 4 edges.
Yes.
And we have 4 vertices.
Yes.
But 4C2.
No, there is nothing called 4C2 by the way, it's 4 choose 2. That was the question, what is the maximum possible edges? What's the maximum possible edges, right? So if you, here are other pairs are possible. So for example, BD is possible, 4 choose 2 is 6, right? We have 4 edges. If you add BD and AD, then it will be 6, right? So that's the maximum possible size of the graph. This size is 6, right? The size of this graph is 6. Okay, adjacent, incident, endpoint, size, order. Is this clear? Clear? Okay. Write it on a paper and drink that water, okay? You see that technique, right? Do this, very important thing, especially when we develop the next session. Yes?
So the current size is not 6, right? Current size.
There is no current or past or present thing. There was this properly worded question. It said, what is the maximum possible size of the graph? Size is E. I said, what is the maximum value this cardinality of E can take, right? What is the minimum possible? What's the minimum possible size of a graph? What's the minimum possible size of a graph? N? 0, right? What's the minimum possible cardinality of a graph? Can it be negative 10? The size of a graph, can it be negative 17? What can it be? The zero thing, it's called an empty graph. Okay, an empty graph where the edge set is empty, no edges. Thank you. Okay, is this clear? Okay. Okay, so next word that you degree. The degree of a vertex is the number of vertices that are adjacent to this vertex, right? What's the degree of A? Count which vertices are adjacent, how many vertices are adjacent to A. It's called the degree of them. Equivalently, it's the number of edges that are incident on A. The number of edges that has A is one of its endpoints. Okay, one of the two endpoints, if one of them is A, then that edge will count to the degree of this vertex. Is this clear? It's denoted by degree of V, dig of V, right? That's how we write. Sometime occasionally we'll write D of V, we will not write it, but some textbooks write it. So, don't be confused with that, but generally it's used for a density. So, okay, is this clear? Degree of V? In this graph, what is the, okay, not this graph, in any graph, what is the maximum and minimum possible degree of a vertex? What's the minimum possible degree of a vertex? Why 0?
We consider only 1 point.
We consider what?
If we consider only 1 point,
Yes.
the minimum possible would be 0.
Sir,
The answer is correct, but your reasoning is not correct. You're not applying definition. Okay, can you give me a set theoretic definition of this this degree? In the edge set, how would I find the degree of V? You're given the edge set. Picture the edge set 18. Okay, I know bulky 18, but you see this is one edge, then the second edge, then the third edge, right? 19 minus 1 is the right word for it. Okay, 19 minus 1 divided by 2. Just because I asked the question again doesn't mean you have to have some confidence in your answer. I asked, got 19, choose 2 somewhere, right? And 19 minus 1 divided by 2. Okay, so the number of edges will be just, if you have 5 vertices, so from 1 to 2, one edge, 2 to second to third, another edge, third to fourth, another edge, right? So we have 3 edges for 4 vertices. So for 19 vertices, we'll have 19 minus 1 edges. Okay, this is called the length of the walk, right? How many trips you took, how many roads you crossed, how many tickets you bought, right? For every leg of your trip. Okay, a path in a diagram is a sequence of vertices such that every successive pair is an edge, but this sequence is not allowed to have repetition, right? So it's a walk with no repetition of vertices. Is this clear? In this graph is a path A, D, E, F, right? 4 vertices, 3 edges. Length of the path is also called is 3 vertices. Is this clear? So a walk is basically a non-repeating sequence of vertices, a sequence of vertices with no repetition, and every successive pair must be an edge in the graph. Okay, the previous one was not a walk, not a path, because you see the edge A was repeated. In this sequence you can see the edge A was repeated, right? D was repeated, C was repeated. There is a lot of repetition there, right? So, but a path is like more of a, sometimes it's called a simple path, right? But it's a path. It's clear. Length of the path is still the number of edges that you have to traverse. Okay. The shortest walk. Now we have length. You know, so numbers. We like numbers, right? So number. Why do we like numbers? Because we can compare them. There is a total order there, right? So now I have multiple paths. Some have length x, the other have length x divided by 2. The others, it's a very important problem in networks and communication, because generally communication happens through shortest paths. If you are sending an email from here to some other username, they will find in the topology, in the internet topology, they will find the shortest path and route it to this, right? So the BGP protocol and the routing information protocol, they always just compute shortest paths. Okay, here is a theorem that I wanted to do. So we know the length. So let's prove this theorem. The shortest walk out of all the walk that you see, Did I say shortest path? Shortest walk? Shortest walk, okay. Shortest walk will be, must be a path, right? Can you translate it into plain English? What does it mean? Just substitute the word walk and different. Shortest walk must be a path. Every path is a walk, right? Is every walk a path? Why not? Every path is a walk. A walk doesn't have to have repetition, but it could have repetition. So I'm saying if you consider out of all the walks where the first vertex is u, the last vertex is v, and you find the one which is the shortest thing, then there cannot, this must be a path, meaning then there cannot be any repetition. Does it make sense? Right? You are supposed to prove it formally. Here is a proof. Suppose for the sake of contradiction, we assume that there is a walk from u to v, between u and v, and that is claimed to be the shortest path, the shortest walk, but still there is some repetition, right? So if you picture the walk is a sequence, then there is r written there, and then some, after a few more vertices in between, there is r again, right? It's not a pseudograph, so r cannot appear because r is not an edge. So there is r, and then after a few steps there is r again, right? Okay. If in pictures it would look like the path. If I were to draw those red edges, then it would look like this, that I started from the vertex u, went to some vertex, some other vertex, and r, then from r I went to some other vertex a, then x, then y, then came back to r, then went to p and r and z or something. So there, if there is a repetition, then the walk in picture would look like this, right? And now this is claimed to be the shortest walk. Do you see any contradiction here? Yes.
Okay, so the walk from R to the cyclic thing, would that be a path or
Let's
if
see.
there's no repetition?
No, I'm proving this thing, right? This is proof is going on. We'll come to your questions in a minute. Somebody claimed that I have the shortest walk between u and v, but it has repetition, right? It has some repetition, some vertex r is repeated, but it is the shortest walk, right? And I'm proving that it cannot happen, right? I say, okay, let's look at the walk. This is, you claim this walk is the shortest walk between u and v, right? What is the length of a walk? The number of edges, right? So here from r you went to some vertex, there must be, you consumed one edge, right? Then from that vertex you went to some other vertex, you consumed one edge, and then some number of steps you came back to r. What if I remove this sub walk, this subsequence from r to r? Is that a walk in the graph? If I remove these red edges or these red vertices from the sequence, is that still a walk? Remove this red thing. Is this green thing a walk from u, between u and v, right? What is the length of the green walk compared to the length of the green plus red walk? Which one is bigger, which one is shorter, which one is longer? The pure, yes please? The pure green one is, without the red one, is definitely shorter, right? Because we removed some number of edges, right? So now we have a smaller number, right? So that's a proof of this thing. The shortest walk must be, the shortest walk from u to v must have no repetition. And that means must be a path, right? So a formal proof would just work with sequences, right? Rather than just this picture, because pictures, you understand the graph theoretic, this is a beautiful thing about graph proofs, that in pictures they make really a lot of sense and they are good enough proofs if you say, if you can write it a little bit. But in this case, you will actually, so suppose there is a walk between u and v, suppose u is the first vertex, then a1, a2, a3, a4, and then r, then some ai, aj, ak, and then again r, and then end of the day there is vn, vk, and then finally there is v. So then you take this one piece of at least one edge or at least two edges you will remove for any repetition. Okay, you remove that and you got a walk that is even shorter. Okay, okay. Closed walk, very simple additional concept. So it's called closed walk. Nothing fancy. What is a walk? A sequence of vertices such that every successive pair is an edge, right? It's a sequence of vertex. The first vertex is the first item in the sequence is a vertex. The last item is also a vertex, right? This says if the first vertex in the sequence is equal to the last vertex in the sequence, then we call it a closed walk, right? For obvious reason, you took a closed walk, right? You came back to the starting point. Okay, so it's called a closed walk. In this graph, this is a closed walk. Why is it a closed walk? It begins at A and it ends at A, right? Look at the picture, it looks like a closed circuit, and the sequence, the first vertex is the same as the last vertex, and it is a walk, meaning every successive pair is an edge, right? This AD must be an edge and this BA must be an edge like every other pair, right? Every other successive consecutive pair, right? Every successive consecutive pair is an edge or something like that. Okay? Is clear? Closed walk? So, similarly, for paths, we define what's called cycles, right? You can call it a closed path, right? A path is a sequence of vertices with no repetition. Every successive pair is an edge. A closed path or a cycle is a sequence of vertices. Every successive pair is an edge, no repetition, and the first vertex is the same as the last vertex. So, this no repetition is qualified except for the first and the last one. Okay? So, look at this. There is no repetition except for the first and the last one. Nothing in the middle repeats. Okay? Now, why do we still call it a path or a closed path? Because this A actually is written for our understanding, right? There is an edge from B to A. This A is the same as this A, right? So, it's like this cycle back. Is this clear? So, walk and closed walk. You understand the concept. Repetitions are allowed. The rest everything is the same, right? Walks. And the first vertex in the same as the last vertex is called closed walk. And then the corresponding concept is a path, and here the corresponding concept is the cycle. Okay, a path and a cycle, the most important concepts in graph theory that we are going to study. Okay, a very fundamental thing, because graphs are used to model communications, right? Pairwise interaction, and interaction happens through paths, right? And that's why we call it this thing. So, and similar to the previous theorem, we said we are going to, this is now for today's ICPs, you can think of it as a take home ICPs. Okay, do this at home or because they are a little longer. So if I look at all this, like walks, closed walks, paths, cycles also have lengths. It's the number of edges involved in that sequence, right? So if I look at all the cycles, all the closed walks from A to A, from V to V, from U to U, right? And consider the one which is the shortest, which is the least length. That must be a cycle, meaning that cannot have any other repetition other than U and U, right? And again, if there is a repetition, I can remove it and get an even shorter thing, right? So, simple proof by contradiction. Okay, clear concept? 4 words: walks, next word, paths, closed walks, cycle. Okay, out of all of them, we'll mainly focus on paths. Okay, the walks are just so that you're familiar with the words. Okay, so connectivity, again I told you, connectivity, communication is where graphs are used, what graphs are used for, right? So this is the very important thing which is based on paths, right? Okay, and this is where people make a lot of mistakes. Last time I told you this connected word, people confuse it with adjacent word, right? So do not make this mistake. Okay. Okay, if you have an undirected graph G, I say that the vertex U is connected to the vertex V if there is a path between U and V, right? U and V are connected if there is a path between U and V, if there is any path between U and V. Okay, again, do not mix up with this thing between being adjacent, and try to think of this thing, right? This always, I tell you, we began almost the course with this sentence that P implies Q is not the same as Q implies P. Think of it, those things. Adjacency implies connectivity. Connectivity not necessarily means adjacency. Okay, if A and B are adjacent, is there a path between A and B? Where is the path between A and B? A path is a sequence of vertices, just the sequence AB, right? Successive pair, it's an edge. So if AB are adjacent, A and B are adjacent, then A and B are connected, right? But if A and B are connected, they don't necessarily have to be adjacent, right? So it doesn't mean connectivity could be like multi-hop connectivity, right? Long-term connectivity, indirect connectivity. So in this adjacency meaning like one-step connectivity, one-hop connectivity, okay? Okay, so look at this graph. Do these ICPs, this is just to, they don't take time. In this graph, are C and D adjacent? Is the pair C and D adjacent? Why? Because CD, in a civilized society, if you make this mistakes while it's still written on a board, seriously, it will be punishable by death. If I ever get this authority, anybody makes this mistake so quickly after I repeat, I will chop off their head, right? Nobody deserves to live if they make these mistakes. You understand that, right? That's a civilized society. We are in LUMSx. So don't make this mistake, okay, unless you want to get your heads chopped off. So which unfortunately we can't do. Okay, are C and D adjacent? Why? Yeah, there is an edge, right? Adjacent means is there the question is, are C and D adjacent? The question is the edge CD in the graph, right? Is the subset CD part of the edge set, and we see it is, right? We drew it there. Are C and D connected? Why? Are C and D connected? Why? Where is the path? Yeah, the edge CD is also a path, right? If they are adjacent, they must be connected, right? Now, are A and G adjacent? Quickly, are A and G adjacent? Why not? The edge AG is not there in the graph. But are A and G connected? Right? A and G connected? Why? Where is the path? Quickly. ADG. Look at this sequence. ADG. AD is an edge and DG is an edge, right? So this is a sequence. The first vertex is A, the last vertex is G. So it's a path between A and G, right? So A and G are connected. Okay. A few more. Are C and D adjacent in this graph? Again, this is a non-example of something, so we'll see. Are C and D adjacent? Are C and D connected? Are B and C adjacent? Are B and C adjacent? Are B and C connected? Are E and E connected? A and E connected? Are A and E adjacent? Are A and E connected? What are you laughing at? Are F and G connected? F and G adjacent? Are they connected? Yes? Clear? Adjacent and connected? Okay. Are A and E connected here? How about A and F? A and F are not connected, right? Are they adjacent? Okay. If A and B are not connected, then they cannot be adjacent, right? That's the contrapositive of the statement. If they are adjacent, they are connected. Clear? Connectivity. Do not make this mistakes, right? Do not make this mistake. Connectivity and adjacency are totally different things. Know what connectivity means, right? In pictures, generally it's very clear, but you know, just substitution of words. Is there a path between A and B or U and V, right? Is there a sequence of vertices such that the first vertex is U and the last vertex is V, and every successive pair is an edge and there is no repetition because I'm looking for paths, right? Okay. So adjacency and connectivity should be clear. Now let's see. A graph is connected. We say a graph, an undirected graph is connected if every pair is connected. If no matter which vertex you choose and any other vertex, they must be connected, right? So all pairs are connected. Okay, you think of this diagram in the picture. If A wants to send an SMS to G, can A send an SMS to G? A message, an email, if it was the email network, right? Or ping network, a computer network. Can A this was the web graph, every vertex is a web page. While browsing A, can you click on a hyperlink to go to some other page and then click on another hyperlink to click on to reach some other page? Those hyperlinks are encoded by edges. Can you browse from A to G? Can you start browsing the page A and then end up at the edge at the page G? So can A send an email to this, right? So A and G are not connected. So when we say a graph is connected, that means everybody can communicate with everybody. Every user, every node can send a message to every other node, right? They are, all pairs are connected, right? So in this example, are the vertices B and C connected? The vertices B and C adjacent? Answer my question. Are the B and C adjacent? Are they connected? Is every pair connected? Why not? Sorry? Is every pair in this graph connected? Every pair, why not? Huh? A and E, just one example, one counter example for connectivity. So A and E are, C and E are not connected, right? There is no path between them. Is the graph connected? The graph is not connected, right? Okay, look at this graph. Are A and G connected? Is every pair connected? Is the graph connected? In this graph, everyone can reach everyone. Everyone can send a message to everyone else, right? Is this clear? Connectivity is the most important thing, again, for every practical application and for the course and for the whole theory of graph theory. Connectivity is the most important thing that we study, okay? Because graphs model communications, okay? Okay, so we know what is undirected graph and what is undirected graph connectivity. Here is one more related concept. It's called the connected component, right? So if the graph is not connected, then we still want to do some analysis of this, and not connected graphs are also used for many things, right? So a connected component is a subgraph that is connected. Basically speaking, it's a subgraph that is connected, right? Why don't we call it a connected subgraph? Well, that's why the word component comes from. It's connected component, not connected subgraph. We know subgraph, right? It's a subgraph that is connected, but it's maximal, meaning it's the largest. Not the largest. It's as big as it could get, right? So the maximum. I told you many times, I guess, the difference between maximality and maximum. What is the difference between maximal and that you cannot make it bigger. Maximum is just looking at it from outside, and out of all these pieces you choose the one which is larger, okay? Maximal is like you cannot grow. Maximum is choosing the biggest one, right? So different concept. Look at this thing. Look at the subgraph ABCD. Is this a connected subgraph? Right? Look at the subgraphs EFG. Is this a connected subgraph? Is it a subgraph of the bigger graph, right? The overall 7 vertices graph. EFG is a subgraph and it is connected. So I say this is one connected component of the graph. This is another connected component of the graph. Okay, there are 2 connected components in this graph. Now, if I was to choose, look at this graph. So is the graph connected? Quickly, we saw it earlier, the graph was not connected. Is the subgraph EFG a connected component? Is connected? The subgraph induced by EFG is connected, right? Is the subgraph induced by EFG connected component? It is a connected component. If I take EFG, it is connected, it is a subgraph, it's a connected subgraph. Can I add any other vertex to it without destroying connectivity? I cannot add any more vertex to it without destroying connectivity. Is the subgraph ABC connected? Is the subgraph induced by the vertices ABC, is that connected? Look at ABC, are they connected? Why? Are A, B connected? They are adjacent, right? Are AC connected? They are adjacent. Is BC connected? Yes, there is a path from BAC, that path is. So ABC is a connected subgraph, right? The subset of vertices induce graph. I don't have to tell you edges. When I tell you vertices, edges are given, right? So it's the induced graph, the graph induced by, the subgraph induced by vertices A, B, C is connected, right? Is it a connect? Can this component grow? Can this subgraph grow while still remain connected, right? I can add the vertex D to it and still component ABC is a connected subgraph, but it is not connected component. Okay, so that's the word maximal that you should make clear. Is this clear? So in summary, a pair of vertices is connected if there is a path between them. A graph is connected if every pair is connected. Okay, and a connected component of an undirected graph is maximal connected subgraph is called a connected component. Okay, so when we are working, we know the internet topology, we know the web graph topology, we know the social networks, we know those are not connected graphs. For the billions of vertices, they are not connected graphs, right? But then there are internal, correct. So I know the CIA has a network on with subgraph of the internet. It's not connected. Internally they are connected, but nobody can reach that network, right? They made sure that their network is totally separate, not reachable from the rest of the thing, because otherwise people would hack into that. Right? There are ways to deal with those things. So people make these isolated components. Many proprietary networks have their own proprietary internal networks. It's a subgraph, right? Some subset of vertices of all the internet. Everybody who's ever connected through any means, there is a subgraph there. But it's connected component by itself. Nobody can reach them from outside. They cannot reach anybody from outside to outside, right? Okay, so here is a good way to write to define a maximal connected subgraph. It's a subset of vertices in which all pairs are connected. That means it's a connected subgraph, right? But no other vertex can be added without destroying connectivity, right? Unless for it to remain connected, I cannot increase it, I cannot enlarge it. Okay, so the connectivity is good, we're done with that. So now let's do connectivity of directed graphs, right? What is connectivity? Because graphs could be directed and undirected. So in undirected graph, U and V are strongly connected. They are called strongly connected. If there is a path from U to V, I told you earlier, when it's a directed graph, then the first vertex is U of a sequence of vertices where every successive pair is an edge, and the last vertex is V. That is called a path from U to V, right? And the path from V to U is when the first vertex is V, the last vertex is U in the sequence, and every successive pair is an edge. So in a directed graph, U and V are called strongly connected if there is a path from U to V and a path from V to U. Okay? Previously, for undirected graph, we said a path between U and V. Now it's a path from U to V and path from V to U, right? So U and V are strongly connected. If U can talk to V, if U can send a message to V, and V also can send a message to U. Okay? If it helps, slightly informally, strongly connected could be reworded as bidirectional connectivity. Okay? If U and V are connected bidirectionally, then we call it strongly connected. Okay, very informal thing. Okay, is there a path from A to E in this graph? Is there a path from A to E? Where is the path? Where is the path? A, C, E, right? There could be many paths, right? There is another path, no other path, right? Okay, A, C, D, B, A, C, E, that's a walk, but not actually a path, right? Because there is repetition. We go from A back to A and then go from C to E. So, is there a path from E to A? Can E send an email to A? Right? How? E, D, B, A, right? So, are A and E strongly connected? They are strongly connected, right? Here is a next graph. Is there a path from A to E? Is there a path from A to E? No. Is there any sequence of vertices such that every successive pair is a directed edge in the graph where the first vertex is A and the last vertex is E, right? Is there? So A, there is no path from A to E, right? Is there a path from E to A? Right? E, D, B, A, exactly the same as above, is still a path from B to A, is from E to A, right? Are A and E strongly connected? They are not strongly connected, right? In some cases, there may be no connectivity between them in either direction. But in this case, at least there is no bidirectional connectivity between A and E, right? Okay? Okay. So a graph is called, a digraph, a directed graph is called strongly connected. The whole graph is called strongly connected if every pair is strongly connected. Okay? Just like in an undirected graph, we said the graph is connected if every pair is connected. Now here, a graph is connected if everybody can reach every other node, right? Every node can reach every other node, right? Because a directed graph, A to X, B reachability may be different than B to A reachability, right? Okay, in this graph, are C and D strongly connected? C and D strongly connected. How can D reach C? How can C reach D? That's one way. Is there any other way for C to reach D? There is. We said there exists a path, right? So the CD is one path. This one hop path, one path of length 1. There is CED. It's another path, right? So C is connected to D, right? In some sense, C can reach D. But are C and D strongly connected? Can D reach E? Can D reach C? Right? D, B, A and C, that's a path from D to C, right? So C and D are strongly connected. Are all pairs strongly connected? Are all pairs strongly connected? Is there any vertex which cannot send a message to any other vertex? All pairs are strongly connected. Check them. You can see AC and CA, AB and BA, ABD and DB, right? And all of them. There are ways to find out. We don't have to do this pairwise analysis. We don't have to manually check for each one. We'll see how to check if a graph is strongly connected, right? This is your data structure. One of the first things you will learn in data structure course is strong connectivity testing. Okay. So are all pairs strongly connected? This graph is strongly connected, right? Okay. This other graph is C and D. Are C and D strongly connected? C and D not strongly connected? Can D reach C? Can C reach D? C and D are strongly connected, right? Are all pairs strongly connected? Which pairs are not? Give me an example pair which is not strongly connected. A, B, right? B can reach A, but A cannot reach B, right? There is no path from A to B. So A and B are not strongly. Is the graph strongly connected? Is the graph strongly connected? Because the condition is all pairs must be strongly connected. And I have found one pair which is not strongly connected, hence the graph is not strongly connected, right? Now, okay, please pay attention to me. When the graph is not strongly connected, which is usually the case, right, in graphs, we don't give up on it, right? There's still very interesting questions we can ask and very interesting analysis we can do. The web graph is it is directed graph, right? A page with a hyperlink to another page you cannot go from that page to this page. There is a hyperlink, you can go this. The web graph is inherently a directed graph. The Twitter graph is a directed graph, right? It's no bidirectional friendships. So those are web graph we know is not connected, not strongly connected, but we still do a lot of analysis, right? The page rank algorithm that Google uses, the hits algorithm that ask.com is using, and now Google is also using, the topic sensitive page rank and many other page rank search algorithm, web search algorithm works on the web graphs, and they work with it despite them, right? All pairs within that subgraph or all vertices within that subset of vertices are strongly connected. Okay, so in this graph, these three are the strongly connected components of the graph, right? Yes, please.
So if we could say that, if we think about the components as vertices in another graph, that graph would be strongly connected.
That will never be strongly connected. That's coming in a minute. Okay, that's called the component graph. It's a meta graph, the super graph, the top of graph. That will never be connected because there is a reason things went to this component and not that component. So it will not be connected. That will be DAG. It's coming in a minute. Okay. So a strongly connected component in a digraph is a maximally strongly connected subgraph, right? Subset of vertices, every pair is strongly connected and that subset cannot be enlarged. Okay. So in this case, this is the thing. Here is another more comprehensive example. Is are A and B strongly connected in this graph? Are A and B, the vertex A and vertex B strongly connected? No, right? Because A can reach B, but B cannot reach A, right? Are B and E strongly connected? Right? B and E strongly connected? Yes, B can reach A. There is a path, namely the edge, the BE, and then there is a path from E to B, namely the edge EB, right? Now, is the subgraph induced by JKL a strongly connected? JKL, is it JKL? This is J, right? JKL. Is it strongly connected? Right? It's a triangle. Everybody can, it's a cycle, right? People can reach, everybody can reach every other. Okay, so this subgraph is strongly connected. Every pair is strongly connected. But is this JKL a strongly connected component? Right? So now the word maximality will come. Is JKL a strongly connected component? Activity of a graph, right? So if you have an undirected graph, last time I told you, when I say the word graph, not qualified, that means undirected simple graph, right? If I have an undirected simple graph, and I know that this is not connected, it is disconnected, right? Not connected graph. I know what does not. Now, if I, okay, its complement graph must be connected. Theorem, go home and prove it. It's again, ICPs today are take home. Please work on it, right? It's a very simple thing. Just substitute the definition of connected and the definition of complement, and you will get you should be able to prove. Okay. Okay, so now we're going to do quickly go through some interesting applications of graph. Very few. The graph is just a cool thing, right? I told you this is one of the coolest topics of the graph of the course. Maybe so far the coolest topic in the course, right? Except for next time it will be even better applications and other stuff. So far it's cool. Look at this thing. Everybody should have seen this. This ferryman transportation puzzle, right? So there is a ferryman who has a wolf, a cabbage, and a goat, right? Can you see the diagrams? Yeah, I tried to find good diagrams, so quite clear, okay? Now, he wants to transport all three objects to the other side of the river. Trouble is, can only carry two objects with himself on the boat, on the ferry, right? What shall we do? So, is it clear? The setup clear? Right? So, here is the issue. Boat can carry one object with the ferryman. With the ferryman, two objects can go on the boat, right? Can you please stop talking? Just pay attention to me. We're running out of time for that nonsense. So, the boat can carry only one object with the ferryman, right? Now, if a cabbage is too small, but say some green thing. So if he carries the cabbage with himself once in one trip, then the wolf would eat the goat, right? If he carries the goat, then that's okay. If he cannot leave the wolf with the goat, cannot leave with the goat with the cabbage, and these are the two restrictions. Goat cannot be left alone with the cabbage, and wolf cannot be left alone with the goat on one side, right? Unsupervised. What can we do? More importantly, we graph theory in this. Yes. Okay. What can you do?
Sir, you first take the goat to the other side.
First take the goat to the other side.
You come back. Then I suppose you could take the wolf. Then you go back. You drop the wolf. Take the goat. Take it back. Then you have the cabbage.
You first took the wolf or the goat, and then you took.
So, sir, the idea is that you will have to pick up something after bringing something to this side.
You'll
take one of those things to the other side as well.
Okay. So one of the solutions would be to take the goat. You said goat, right? Goat to the other side, and then come back and take the wolf to the other side, and then come back, bring the goat back, and then take the cabbage to the other side, and then come back and then take the goat to the other side, right? Here is how you can model it with graphs. Okay, here are possible states of the system, states of the affair, right? I'm not going to go in the details of it, but here is this picture. Look at this picture. This setup means the ferryman, the wolf, the goat, and the cabbage, all 4 objects are on this side, on one side of the river, and nothing on the other side, right? Dash mean nothing, right? In this setup, ferryman, wolf, and cabbage are on the left side, goat is on the right side. Okay, and all of this thing. So we begin with this setup, all 4 on one side. We want to end up in this setup, right? All 4 on the other side. Okay, between 2 nodes I've drawn edges. If from this state, legally following those 2 restrictions, that wolf cannot be left alone with the goat and goat cannot be left alone with the cabbage, following these restrictions, can we go from, if I can go from one state to another state, one situation from another to another situation in one trip, I draw an edge between them, right? So these are theoretical, hypothetical possibilities of things. And now what I want to say, to solve the puzzle, I just want to find a path from this system, from this state of the system to this state of the affairs. Is this clear? Find a path, or ask, is this node connected to this node, right? Can I reach from this node to that node? While going through these edges, there are only allowed edges. So for example, there is no edge from this node to this node. What does it mean? There is no way that I can go in one trip from this state of affairs to this state of the system. I cannot do that, right? That's why there is no edge. So if I can find a path from the top right vertex to the bottom left vertex, that means following the edges, that means just do this trip, that trip, that trip. These are all legal states of the system. Okay, so this you can find a path using what's called the breadth first search algorithm, or the DFS, depth first search algorithm. Again, this will be one thing that you will study, one of the first things you will study in algorithms. Okay, here is another thing that will bring me to your question too. This is you must have seen this kind of stuff, right, in your student's handbook or your thing. This is called the prerequisite chart. Typical how a program, a major or minors rules are conveyed to the students or to the potential students is by giving this thing, right? What do we see? Well, except for those laddus, now we have rectangles, but rest of them there are the edges, right? There are lines, directed lines. It's actually a directed graph, right? This is for Florida State University, if I remember correctly. Yeah, FSU. For the day I was making this thing, there was some issue there. There was in the news somehow, so I just got their computer science prerequisite flow chart. Okay, it's called prerequisite flow chart typical. This is clear, right? This is, everybody can understand this, right? This means intro to probability is a prerequisite of analysis of data structures in algorithms. Intro to probability is a prerequisite of theory of computation. Intro to probability is intro probability is only analysis of algorithm. Calculus 2 is a prerequisite of analysis of probability. Data structures in algorithms and general programming is a prerequisite of programming languages. Okay, so that's what this means. I have a question. Can this graph have a cycle? We know cycle, right? We know graph, we know cycle. It's a directed graph. Can there be a directed cycle in this graph? Can there be a sequence of vertices? Every successive pair is a directed edge. The first vertex is the same as the last vertex. If there is, what would it mean?
Something is repeating itself.
A higher level course is a prerequisite of a lower level course.
What is the high and low level?
Yes, like if calculus.
How do you define high level course? The highest level course, what would that be?
Sir, like for example, if calculus is a prerequisite.
No, not for example. Answer my question. How would you define the highest level course?
With the longest path between.
So it will have no outgoing edges.
It will not be prerequisite of anything, right? It doesn't feed into anything. Now, if there is a cycle, what is the highest level course or the high level or low level. Okay, but you're right, the thing is there cannot be a cycle in this graph, because to take the course A you must take course B first, to take course B you must take course C first, to take C you must take A first, and you're stuck, right? You cannot do anything, you cannot break this cycle, right? There cannot be. So directed edges represent prerequisite. Can there be cycles in this graph? No. These graphs is what's called directed acyclic graphs, right? Directed acyclic graph. Now if you take a directed graph, you find its strongly connected component and you kind of zoom out of this, or you merge that connected component into one super node, meta node, or this super node is called super node. We use it a lot in graph compression, this super node and super edges. And so this is called the component graph. The component graph of any directed graph must be a directed acyclic graph. Again, because if there is a cycle between the components, then these components should all belong to the same strongly connected component. This should be one component, right? That was the question you asked. The component graph cannot have a directed cycle. Okay, it will be called directed acyclic. These are called directed acyclic graph. The second thing you would study when in data structures and algorithm, or both of them, will be the so-called topological sorting algorithm. Sort, linearize, induce an order on the vertices of the graph. Tell me, in what sequence can a student take these courses? That's called a topological sorting. Topological sorting is an ordering of vertices such that all edges go from left to right, right? So that's a feasible order. There could be multiple topological ordering. So one student can fulfill all these requirements while taking courses in a different order than some other students, right? So a topological ordering is found through DFS. Connected components are found, strongly connected components are found through DFS, this depth first search algorithm. Here is a cool thing, some big words and not now big concept. We're not going to talk more about it, but I just want to define it because graph design, network design is a very important branch of graph theory, network design, and these type of questions we ask, right? A connected graph is called connected graph. We know it's a connected graph, right? Everybody can reach everybody else. It's a robustly connected, it's a securely connected graph. We call it K connected graph, that even if I remove K minus 1 vertices, any K minus 1 vertices, the graph still remains connected, right? Even if K minus 1 nodes break down, the internet will still be connected, right? It does happen all the time, right? This is called fault tolerant computing, right? Resilience, you add resilience to the designs, it has robustness to the design, right? A cut vertex, a vertex that really is what's called a cut vertex, that if I remove it, the graph becomes disconnected, right? So look at this graph. Suppose somebody, you want to design a network, you want to you want to install cables or some wireless connectivity in your system. You want to connect these how many vertices are there? 8 nodes. Very bad design. It's not going to, not serving the purpose. Look at the first one. The first one you said is the best, right? Look at the first one. If this one router is broken, you're doomed, right? You cannot talk to, right? You cannot do this. Look at this one. This was the cut vertex. This is called, by the way, a cut vertex, right? This, you cut it. If you remove it, then the graph is broken. Look at this one. Every vertex is a cut vertex. You take any vertex down, you are done, right? You are done, the connectivity. This is a very robust design. This is a one connected graph. Any deleting, removing, breaking any one vertex will still keep the network alive, right? It will still be connected. So this is a one connected graph. This is a disconnected already. All of them are like kind of one connected, zero connected graph, right? Is clear? Okay, so this is how connectivity is used for, and this. Okay, so this you must have seen. I think we talked about it in the first day, right? So you want to tour this city such that you want to cross, you cross every edge, all of these 7 bridges exactly once, right? Is it possible to tour this city like that? Right? This was one of the earliest results in graph theory that we saw, we discussed in the first day. Here is another thing. Can you draw this picture without retracing any piece and without lifting the pencil? right? What does it have to do with connectivity? Can you draw this picture without retracing or lifting the pencil? Yes? Why? If, again, yes, no is not important. Graph theory is important. So at some point I gave a talk in some place. The title of the talk was, what if we had a negative number of fingers, right? So it was the number system, so why do we use decimal number system? Because we actually have 10 fingers, right? So we got used to that thing. But if we had 2 fingers, meaning if you were working a base 2 numbers, it will be clear, right? You can work, computers work with that thing. Any base system, you can just do computation. If we had 8 fingers, still life would be okay, right? So can we do this question? So the talk title was this: what if we had a negative numbers of fingers, meaning negative base number system will work or not, right? And it turns out, yes, it works. Totally good. Everything is cool. We can do all the algebra, all the arithmetic, and it will work out. It turns out that for the large part, even if you had a complex number of fingers, right, a plus 3 iota, it still will work, right? So that was the talk I gave. So I had a Russian friend, it's a very famous, what is it called? Aqual is attributed to him. A very blunt guy. And so I was telling him that, okay, look, what if we had 2 fingers? And then he did this calculation, very good in math. He said, oh, yeah, okay, we can figure it out. And I said, what if we had 8 fingers? He did this, oh, okay, just increment this thing and just do this thing, and figured it out. And then I said, what if we had a negative number of finger? And the guy just got confused. So he did this. And he said, no, as long as I have that 1 finger that I can use for traffic signals, I'm okay, right? I don't care about that. So if you know Russian, they use that traffic signals a lot, right? So this was reminded to me from because of you guys were doing that thing. Okay, can you tour this? This is a museum. This is a art gallery or something. Can you enter this room, this door, and exit through this door while going through every door exactly once in this building? Can you traverse every door of this building exactly once, entering from this door and ending? So these are doors. This edge and this edge. You see this edge is counting again, right? So that's what I added 3. Each edge is, this edge is counted twice. Then when I added this 2, where is this 2 coming from? Because of this edge and this edge, right? You see this edge is counted twice. Then when I add the degree of this 2, the degree of this vertex, which edge is where I'm counting? I'm counting this edge and this edge, right? You see all edges are counted twice. Is this clear? Okay. So another a little bit more derived, what is called piece of derived information from the handshaking lemma is that if you look at all the degrees, some degrees will be odd, some vertices will have degree which will be an odd number, some vertices will have degrees that will be an even number, right? How many vertices could have odd degrees? That must be an even number, right? An even number of vertices can have odd degrees. Okay, and that's because in total they have to add up to an even number. So if there were odd number of vertices will have odd degrees, so odd times odd will be an odd number, odd plus even will never give me an even number, right? It must be an even number of vertices must have an odd degree. It's a simple derived version from these 3 pieces of information. All of these 3 things are exactly the same statement, right? Exactly the same statement. This one is just a little bit more precise. The rest of the stuff, the first and the third one is exactly the same thing. I can say it in many different ways. Okay. Again, look at the previous examples. I wanted you to make 5 vertices whose degree are 3. This theorem says an even number must, the number of odd degree vertices must be even. You wanted me the number of odd degree vertices to be 5. That is not an odd number, not an even number, right? Okay. So to go home, I have talked a lot about it and I don't have time. So please complete this thing, okay? Hopefully you understand this thing. give a formal proof. I gave you formal proof of this. This is actually the formal proof of this thing. Okay, this was an example, but if you just add up degree of V1 plus degree of V2 plus degree of V3, then some edges will be counted, each edge will be counted twice. For directed graphs, there is also a handshaking lemma. Adds up to a little bit different thing. In directed graph, the handshaking lemma says that if you add up all the even degrees, all the in degrees, you get a number. That number must be equal to had you added all the out degrees, right? So the sum of the in degrees must be equal to the sum of the out degrees. Does this make sense? That is even simpler to see, right? Because each edge contributes 1 to some in degree. An edge from A to B contributes 1 to the in degree of B and 1 to the out degree of A, right? Each edge is counted once from this side and once from that side if you are adding the sum of, if you are calculating the total, the sum of odd degrees and the sum of even degrees. The sum of out degrees and the sum of in degrees. Okay? Clear? Nothing else. Okay, I just did this thing. This is even simpler because okay, in some applications we require, please pay attention to this. Okay, this is important because I'm going to begin graphs application. The next concept, the next is very conceptual, and people just find extremely, I told you this adjacent word, when you heard the word adjacent, I asked you to really drink that soaked water, because that is what the confusion comes, and that's connectivity is what the word that people confuse with adjacency, and you will lose a lot of, you'll have no understanding of graphs if you confuse those two words. Okay, so I'm going to go to that just to wake up. In some cases we require weighted graphs. Okay, weighted graphs. These are called weighted graphs. So in this case, a graph has three things. Edge weighted graph has three things: set of vertices, set of edges, and a function, a mapping from the edges to real numbers, right? So it's written like this: G, V, E, and W. So V is a set of vertices as usual, E is a set of edges or directed edges if it's a digraph, and then we have a weight function, which is called weight function, or we have a weight function or cost function or fare or some kind of function that gives every edge some number, right? Every edge gets exactly one number, right? It's a function. Okay. Okay, so this is how we depict the graph, a weighted graph. We see this is the edge. What does this line depict? This depicts the directed edge from D to E. This number is the weight of this edge, right? This number is the weight of this edge, the edge DG, right? The top number 3 is an edge, the weight of this edge S to A. Okay, every edge gets exactly one number is a weight. Okay, it's called the weight function. So sometime we work with weighted graphs. Okay, and I will show you applications where we do. Sometimes we work with vertex weighted graph, or sometimes vertex labeled graph, sometimes with vertex, it's called attributed graphs, right? Look at this. If you look at Facebook and you restrict it down to LUMS, right? Every user will be a LUMS student, let's say LUMS student, right? You ask Facebook, give me the data of every LUMS student, right? You'll get their profile and you'll get their friendships. Now, any friendship from LUMS person who is friends with MIT person, you don't look at it. You just look at it, the local version of the Facebook graph, right? The LUMS, this is called Facebook restricted to LUMS. Okay, a graph restriction is a very well-known thing. We work with some pieces of graph. I have the word for it, but next time in next slide we'll describe it. So it's called the subgraph. So is this clear, right? How many users this graph have? How many? 8, right? Edge means friendship. There is this attributes, these extra properties, characteristics of each user. It makes sense. This is a characteristic. Every person has a gender, every person has age, a major, and an ethnicity. It could be boarding hostelite status. It could be level also. Is it sophomore, junior, freshie? What is it? A graduate student, undergraduate student? Is it major is done. Maybe minor is another thing, right? Maybe high school. Where each high school did this guy come from? Maybe which city does he come from? Does he live on campus? Does she live on outsider, commuter, daily commuter? Yes, quickly. Yes, vertices के attributes. If they are generally the edges, there are some types of so people use edge labeled graphs also. Then edges attributes could be. So let's say if it was a call graph, then A called B, but what was the length of the call? What was how long did they talk, right? What was the cost of the call? What was the network used? What is the topology? Which base station was used? Which antenna was used? Right? Which frequency was used? And many other things could be there. This is, but generally we need one number for weighted graph in many applications. Yes.
In this case, maybe how long they've been friends on Facebook.
This could be, but this is now vertex with each vertex. It's not a pairwise attribute, right? This because I made this diagram. A year ago, I published a paper on this on attribute prediction. In Facebook, people hide their profile, right? They think nobody can find out. We have a paper on ACM transactional intelligence systems and technology. We know everything about you, right? Facebook knows even more than us, but they're now using partly our work to find out who you are. So even if you hide it, even if you don't disclose it, we can find out, okay, who you are. Not because of doing some other analysis. Just looking at your friends, I can find out, right? There is a whole concept of social selection and social influence. From this we can find out, okay. So those people, when I worked on a DC, people would say, oh no, I was not smoking, these people were smoking, I was just there, right? I was just sitting there, I was just enjoying, and because that's actually gave me the idea of working on this thing, and that gave me this idea of this problem. Let's see what can I find out about your major just looking at the major or the age or the hostel status of your friends on Facebook, right? So Facebook provided us data with specific universities, Caltech, Cornell, and many other universities. It's called Facebook 100 universities. And we worked on many other graphs and many other data, some Slovakian social network from that, and some other co-authorship data and stuff. We found out in every case, we can find with very high accuracy who are these people, right? Just because, is anybody seek Pashto? Yes. What? Go ahead.
The question was that how would you find these, predict these sort of things? Would it be done using a machine learning model?
Yes, we do a machine learning and we find out. So the reason, so security will be interested in it. Businesses are interested in this, right? They want to know who you are so they can serve you better, right? You know, they are dying because they want to serve you so well. So Facebook will be selling this data, or other companies will be selling this data to, if they think you would be interested in Nike shoes, then Nike will send you their advertisement, right? They will tell you, okay, buy these shoes that are worth $100 for $500. We'll give you for free $5 rebate, right? And all kind of stuff they will do. Okay, so what's some more thing about graph? When you actually work with a computer with a graph, you will need this stuff, okay? So we'll talk about connectivity maybe. Let's see one more thing about social networks. We all do this. You ever heard of the small world phenomenon in social network or almost any network? Small world graph. Small world graph. How many? Tell me any. Okay, yes.
Sir, there was something like degree of 6, 7.
the 6 degrees of separation and this kind of, yes.
Connected to every person by 6 legs.
So let's say so we are thinking of handshaking. So think of any person in Pakistan, any person that you know it, but you think is very far from you, right? Like you have heard name or something, but very far from you. Or anyone. Think of any person in Brazil. Okay, let me just tell you this thing. You know US President Biden, right? They had a dog with the name Major, right? The Major was born to some other dog, right? So Major's parents' dog, their owner, next door neighbors. Think of that person. Does it make sense? Biden's dog's parents or father, which was another dog, the owner of that dog's next door neighbors. Do you think you would know that person? Let me just tell you, how far do you think, how many handshakes away is that person from you? So you shook hand with me, I shook hand with them, then he's only 2 steps away from you, right? 2 hops away from you. Let's assume it's very likely that neighbors would have shaken hands with the dog's owners, right? That guy would have shaken hands with Biden, right? Biden most probably would have shaken hands with Imran Khan, or if not, then Biden shook hands with Nawaz Sharif generally because he was the vice president, or Nawaz Sharif must have shaken hands with Imran Khan, right? So that dog owner's neighbor was only 6 steps away from you, 5 steps away from you. That makes sense, right? So who is any of your favorite soccer players? Any favorite soccer? Messi? Okay. Huh? Ronaldo. Okay. Okay. So the father-in-law of Ronaldo's other daughter's father-in-law's neighbors. How far away is that from you? How far do you think is Ronaldo from you? How far do you think Ronaldo is from you? 100 steps? Really? 100 steps? I don't. So do you think Ronaldo shook hand with the owner of An-Nasr club? Yes? Most probably did somebody in An-Nasr club, right? An-Nasr is a big club and they are the owner of the club. Does it make sense? Do you think they shook hand with any of the royal families, the Mohammed bin Salman, or right? Do you think Mohammed bin Salman shook hand with Imran Khan? This guy shook hand with Imran Khan. You shake his hand, you are 5 steps away from him. Ronaldo, right? And Ronaldo is 4 steps away from that thing. This is really, really a small world, right? There may be some isolated person somewhere in the Sahara desert that this whole community never went out of it, right? But if you think of acquaintance, this is called the small world phenomena, right? I just took handshake as an example of thing. Anybody, I mean, I shook hand with Imran Khan, I shook hand with Nawaz Sharif, I shook hand with not Zardari, I guess, I don't know. But I shook hand with this Zulfikar Ali Bhutto, that the Murtaza Bhutto's son, Bilal's first cousin, right? So most probably they shook hands sometime, right? I shook hand with Nawaz Sharif shook hand with Zardari, I shook hand with Imran Khan must have shaken hand with Zardari, right? Nobody is far from you. Nobody is far from you, okay? So small world graphs, and this is actually sociology people study these online social network to see an approximation. Yes?
Sorry?
Sorry?
So I just got the connection. How can I shake hands with Ronaldo?
How many handshakes Ronaldo is away from you?
I shake hands with an instructor.
With
Instructor shakes hands with Said Babur Ali. Said Babur Ali probably has shaken hands with some prime minister. That prime minister has probably shaken hands with Mohammed bin Salman.
Yeah.
Or some other
So
sort of
that's what that's where I came from. That a Nasser owner would be, you were sleeping, na? Nasser. You know Maradona? How many of you know Diego Maradona? I shook hands with him. I think he met Cristiano Ronaldo. So you're not very far from Ronaldo. Okay. Huh? Sorry? What did you say? I met him once in the US sometime. He was my favorite player. How would I represent an undirected graph, okay, in a computer? How would I feed for any analysis or any queries or any processing? What will I do? How will I feed it to a computer, right? Computer cannot see the Laddu and Lakire, right? That's not the computer's thing. Computer needs numbers, right? Zeros and ones. So one way to represent this is what's so-called adjacency matrix. Okay, an adjacency matrix, it's a matrix. I have one row for each vertex. I fix some ordering of the vertex, some labeling, some ordering of the vertices. This is the first vertex, the second vertex. So then I have one row for each vertex. The first row is for the first vertex, the third row is for the third vertex, the ith row is for the ith vertex, and one column also in that order for each vertex. Okay, and this is a binary matrix, a 0 1 matrix. Each entry is either 0 or 1, and if ij is an edge, in ith row in the jth column I put a 1, and also in the jth row and the jth row and the ith column, right? So it's an undirected graph. So, okay, look at this graph. How many vertices? 8 vertices, right? So I will get a matrix of 8 rows and 8 columns. Okay, the first row I've written the labels of the first row corresponds to the vertex A, the second row corresponds to the vertex B, the third row corresponds to the vertex C, and so on, and similarly columns. Is this clear? Now because there is an edge, the edge E1 is between A and B, so in the row of A and the columns of B there will be a 1, right? And similarly the row of B, A, B is there and B, A is there, the rows of B and the column of A, there will be a 1 here. Okay, so if there is an edge between a pair, the corresponding row column pair will have 1, otherwise it will be a 0. Is this clear? Representation clear? Okay, when you say something is clear, so I'm going to ask you a few questions in a minute and then we'll come back to this. Okay, is this clear? Okay, here is adjacency either graph and is adjacency matrix of this graph. If the graph has n vertices, what will be the dimension of the how many entries in this matrix A? Huh? If the graph has n vertices, how many entries will be there in the matrix? Huh? Yes, how many? N times n, right? N times n, n squared. It's clear? Okay, how many ones will be there in this matrix? If the graph has k edges, how many ones will be there? Huh? K?
N squared minus n because the main diagonal will be 2 and 2.
If the graph has 2 edges, there will be 1 edge, then there will be only 2 ones. 1 signifies the existence of an edge. Look at this. Not this graph, any graph on n vertices, depending on the number of edges, that's what we'll see the number of ones. In this graph, you said n squared minus n, right?
Maximum amount.
That's the maximum. So I'm just saying for any graph there will be, that's the maximum we saw at the maximum possible size of the graph. If the graph is 2 edges, how many ones will be there? 4, right? Because each edge is written twice, right? One in ij AB entry and one in BA entry. Okay, how many zeros will be there?
N cross n minus.
How many edges will be there? No, I'm not explaining, it's a question. You are going to answer it. How many edges will be there? How many edges? The graph has 10 edges. How many ones will be there in the matrix? Why? Okay, look at this graph. How many edges are here in this graph? 5. How many ones are there in the matrix? Why? Yeah, because each edge is written twice, is mentioned twice in this matrix. Once in the, because there is no undirected graph, right? So AB and BA both are edges, so we just put it both, right? How many zeros will be there in the graph, in the matrix?
N cross n minus 2 times
Yeah.
number of edges.
Yeah. So if the graph has k edges, the order size of the graph is k, then it will be n squared minus 2k, right? It's just exactly the same question. All entries, ones, zeros will be by the complement principle, n squared minus 2k, right? Okay. What are the diagonal entries of A? Why are the diagonals always going to be zeros? Or just talk about the diagonals. If the diagonal is 1, what does it mean?
It means it's a pseudograph.
Yeah, if AA is an edge, then if AA is 1, that means there is an edge from A to A. It means the graph are allowed to have self loops. It's a pseudograph, right? The diagonals will, how many diagonal entries? N cross n square matrix, it will be n, right? How many ones are there in the row corresponding to a vertex A, vertex V? How many ones will be there in the row corresponding to vertex V? That is the degree of V, right? How many edges are incident on the vertex will be, how many vertices, how many ones in the columns corresponding to the vertex V? Again, the degree of V, right? Is this clear? That's how you understand a concept. Yes?
Can you repeat that? How many ones and zeros? I did not understand.
So each edge, so you see this thing, look at this graph. What does this one mean?
The second one is the edge.
There is an edge from A, the first row correspond to A, the second column correspond to B. There is an edge between A and B, so I put a 1 here. But I also put a 1 here, BA, B row and A row. So for each edge I will put 2 ones, right? 2 times, yes, k was the number of edges. Yeah. Okay, for a digraph we do exactly the same thing. There is a n squared matrix, 1 row corresponding to each vertex, 1 column corresponding to each vertex, right? But now if there is an edge from Vi to Vj, I will put a 1 in the Vith row, in the ith row and the jth column. So now it's just 1 for each edge, a single 1 for each edge, right? Not 2 ones for each edge. Is this clear? In this example, how many edges are there in this graph? 7 edges, right? There are 7 edges in this graph. Yes? How many ones will be there in this matrix? 7 vertices, right? Not twice 7, not 14. Right? Why is this entry 1? Look at this entry. Why is it 1? What does it mean when I put this entry 1? First row is for A, second row for B, third row for C. This is the edge from C to B, right? That's why I put a 1. Is there an edge from C to B? Why isn't there? Why is this thing 0? Why is this thing 0? Sorry? There is no edge from C to A, right? That's why it's 0. Is this clear? Adjacency matrix of digraph representation. Again, let's check our understanding. Suppose I have a digraph on n vertices. How many entries will be there in the matrix? A digraph on n vertices. How many entries will be there in the matrix? N squared. How many ones will be there in the matrix? How many ones in the matrix? The number of edges, right? How many zeros? N squared minus the number of edges, right? That's a simple thing. What would the diagonal entries means? Diagonal entries will mean exactly the number of, if there are self loops allowed, and then they will be there, right? Generally, for simple graphs, we will not allow them, right? And this will be this thing. what will be, this is an important question, please pay attention to it. How many ones will be there in the row corresponding to the vertex V? Degree plus of V, the out degree of V, right? How many edges from V to other vertices? So how many ones in the V's row will be the out degree of V? Okay, what will be the number of ones in the row, in the column corresponding to the vertex V? Degree minus of V. Degree minus is not a word, okay? In degree. Okay, that's just a notation. We don't pronounce it like in degree of V. Okay, the in degree, the number of edges incoming to this vertex, the number of edges where this vertex is the target. Okay. Okay, so there is another representation of a graph of graphs is called the adjacency list representation. Okay, we'll see in a minute why do we need both. The other way to represent the adjacency list representation is basically, instead of just like we saw earlier, that a set can be represented as a bit vector, but the set can be represented other ways, right? So here I look at A and I list the set of neighbors of A, the set of out neighbors of A. I look at B and list the set of out neighbors of B. Okay, so this is, look at the graph. Here is the adjacency list representation, right? So you're not doing data structures now, right? Are you doing now in parallel? Okay, so it's an array of lists. Okay, and each list, it's a linked list and it contains a number of vertices, the number of neighbors, out neighbors, right? For undirected graph, it's out neighbor, and for not undirected graph, it will be just neighbors. Please do these questions and then you can go home. Oh, those we did already. Okay, so just we'll start from this, okay, graph complements tomorrow.